Okay, so we're very happy to start this morning with Sanjaye Ramgoolam. He'll tell us about applied holographic mathematics.
Great. Thanks very much to the organizers for the invitation and the opportunity to speak here at this wonderful meeting. So yeah, I'll be talking about applied holographic mathematics. I'll explain what I mean by this. That will become clear as we go on. Main papers, this is based on a paper recently in September called Quantum Information Processing and Composite Quantum Fields. So some connections between combinatorics of composite fields and some problems in quantum information. And this guy, my collaborator Sedlak, is an expert in quantum information. A closely related paper, which I'll briefly mention, which motivates this paper, is a paper that he did. It's around the same time, but something we have been working on for a while. Interestingly, how I came across my collaborator, Michal Sedlak, we were both at a conference on quantum physics and logic. And the reason I ended up at that conference is because of another paper, which is also applied holographic mathematics, which is linguistic matrix theory. Some kind of new developments in matrix theory inspired by some applications in linguistics. So that will be the subject of the lecture on Monday. And today I will be talking about this quantum information processing. So I should say, please stop me if you have any questions at any time. I hope to go at a leisurely pace, so I'm happy to answer questions at any point. So by holographic mathematics, what I mean by that is some representation theory methods that have been used in the study of composite quantum fields. There were some problems in the half BPS sector of N=4 super Young-Mills having to do with mixing of multi-traces and so on. And these problems were solved using Young diagrams, and there was a result having to do with diagonalizing the two-point functions of arbitrary multi-trace operators with motivations coming from giant gravitons. And that was done in a paper with Antal and Coley several years ago. So basically, this is one matrix combinatorics in connection with Young diagrams and diagonal two-point functions. And this had led to several developments in multi-matrix combinatorics, in particular the definition of what are called restricted Schur operators, where a lot of the students here have worked with Robert and they know quite a lot about this. But there's a kind of subject of restricted Schur operators, and some of the key references are here. And then within this subject of multi-matrix combinatorics, this question of diagonal two-point functions, which is relevant in the quarter BPS sector of free super Young-Mills, was solved in a set of papers around 2008, 2009, with some postdocs at Queen Mary, and also here by Robert and collaborators, postdocs here. And the perspective on this thing that I will be taking is sort of looking at these multi-matrix combinatorics developments using some algebras and the structure of these algebras. So I'll explain what I mean by structure of these algebras as I go on. And this perspective was developed in a couple of papers a few years ago with a student and also by Kimura independently. And as an overview of this whole thing with other applications to quivers and tensor models and so on in a short review. So if you want to orient yourself as I go on where to find what, this is a good slide, and a fairly complete set of references will be here. So I'll now get into the content itself. So I'll be talking about permutation algebras for composite fields. So what do I mean by permutation algebras? First of all, usually we talk. Sorry.
So I begin with those might be three facets.
So you should switch off that voice translator after. So permutation algebra. So more familiar is permutation groups. So it's a finite set of, and in particular the group Sn, symmetric group of all permutations of n objects. And so that's a group, the n factorial discrete elements. The algebra is a vector space with a product. So you consider arbitrary linear combinations of group elements, and then on this vector space you have a product which is inherited from the group product. And that makes this vector space an algebra, which is an associative algebra. So for the problem of one matrix combinatorics and correlators and two matrix combinatorics and correlators, one finds that this algebra and related algebras play a very central role, these symmetric group algebras. So, for the one matrix problem, one algebra which is very important is the center of this group algebra. So this is a vector space with a product. So there is a subspace here consisting of linear combinations of group elements which commute with all group elements. If you multiply them with any group element, these linear combinations, which belong to the center, commute with every other group element in the group. So, and how do we think about the center? Given any permutation sigma, you can form a group average, sigma bar. What is sigma bar? You conjugate sigma by gamma, and then you sum over all gamma. That defines for you sigma bar. And you can easily show that sigma bar times tau, for any tau, is tau sigma bar. So this is one pedagogical bit in my talk. How do you prove this? You put a tau here, and then you have a gamma inverse tau. You call it gamma tilde inverse. You observe that as gamma runs over all permutations once, gamma tilde inverse likewise runs over all permutations once. And if you write all these things in terms of gamma tilde, then the tau appears on the other side. But because both gamma and gamma tilde are running over permutations once, you can rename it, and therefore what you're left with is the same thing, sigma bar, with a tau on the left. So this is the kind of exercise that students can do, and there will be several things like that. I'll let you spot the exercises along the way, and you can prove for yourself things like this. Important thing is that if you average, then you get something that commutes with everything. And it is important that this, for this to commute with everything, it is important that this average is over the whole group, because I want to be able to absorb in that sum, through this redefinition, an arbitrary tau. Good. So sigma bar then is a sum of permutations which are all in the same conjugacy class as sigma. When you conjugate, you get something in the same conjugacy class. And when I do this sum here, I get different permutations within the conjugacy class of sigma, and they all appear with equal weight, it turns out. A given permutation will appear with a weight here more than once, because some gammas will leave this fixed. But it is important that all permutations in the same conjugacy class as sigma will appear with the same weight. So what we're looking at is sums of permutations within conjugacy classes, all with the same weight. So what do the conjugacy classes in Sn look like? Two permutations in Sn have the same conjugacy class if they have the same cycle structure. So if you take the identity permutations as 1 goes to 1, 2 goes to 2, in cycle structure, 1 is isolated in a cycle, and that's the cycle structure. This permutation, where 3 goes to 3, single cycle, 1 and 2 get swapped, that's this cycle structure, where you have a cycle of length 2, cycle of length 1. And all the different ones which have different numbers but the same cycle structure, they belong to the same conjugacy class. So there is some gamma, which gamma sigma 2 gamma inverse will give sigma 3 and sigma 4. So conjugacy class is cycle structure, and the last cycle structure in S3 is the cyclic permutation of length 3. So you see that the number of cycle structures corresponds to different ways of writing your number 3, the n is 3 in this case, as sums of positive integers. 3 is either 1 plus 1 plus 1, 2 plus 1, or 3, and these 3 cycle structures correspond to the 3 conjugacy classes in Sn. And these cycles, of course, have a cyclic property. So here, this I could have written as 1 goes to 2, 2 goes to 1. I could have written it as 2, 1, which would indicate 2 goes to 1, 1 goes to 2, 2 goes to 1, 1 goes to 2. So cycles have cyclicity. And in the application to matrix theory, this will be related to the cyclic property of traces, as we will see later. Now, so we're interested in the center of Sn, of the group algebra of Sn. And what we are saying is that a basis for that center, the basis for the subspace which commutes with everything, is given by conjugacy classes which correspond to partitions of n. So you pick a partition of n, which is a way of writing n as a sum of positive integers. Let's call that splitting of n p. And for each such partition, you can think about the sum of permutations with cycle structure given by P. I'm going to call that Tp. So for example, T2, or the cycle, the permutations which have cycle 1, cycle of length 2, all remaining cycles of length 1, explicitly it will look something like this. I and j are swapped. Everything else goes to themselves. That sum of things, it doesn't live in the group, it's a sum. So it lives in the group algebra. That I'm going to call T2. And anything in the center, anything that commutes with all permutations can be written as a linear combination of these T's. So these cycle structure sums form a basis for every element that commutes with the whole group. That's one basis for the center. There's another basis for the center, which is constructed as follows. Take an irreducible representation of Sn, symmetric group of n boxes or n elements. These representations correspond to Young diagrams with n boxes. So it's a representation. That means for every permutation you have a matrix which acts on the vector space, goes back to the vector space. And if you take the character trace of that matrix, you get the character. And this character is invariant under conjugation. So using these characters, you can build sums of permutations weighted by the characters. And you can, as another exercise, you can show that any permutation tau, if you multiply it by this weighted sum of permutations, you get something that commutes. So, and it is also true that anything that commutes, any z that commutes, can be written as a linear combination of these character sums with some coefficient zr. So now there is a sum over representations, irreducible representations. Here there was a sum over conjugacy classes or cycle structures. So there are two ways to think about the center. One is in terms of a basis given by irreducible representations, and one conjugacy classes. When you normalize these guys correctly, so this chi-r, you put 1 over n factorial times the dimension of the representation, you get something which is a projector. What that means is that if you square this PR times PR, you get PR. And if you have PR times PS, you get delta RS PR. Projectors are important because if you have a direct sum of different representations, this projector acts on the representation on that direct sum. It will pick out those representations which are exactly equal to R. Good, so there are two bases for the center of this non-commutative algebra. Group algebra of Sn is non-commutative. The center is the set of things that commutes with everything, therefore it commutes with itself. So this is a commutative algebra. And this commutative algebra has a dimension, which is the number of partitions of n, and it has two interesting bases, one given by conjugacy class sums or cycle structure sums, and one given by projectors. The projector multiplication is very simple. Two projectors multiply to another projector. The multiplication of conjugacy classes is more complicated. There are some structure constants which have very interesting properties. These structure constants define what is called a commutative Frobenius algebra, which is an example of a two-dimensional topological field theory. So there are two bases for the same thing. Any questions from students at this stage? Great. So the outline of the talk is that I'm going to explain how one uses this commutative conjugacy class algebra in connection with one matrix correlators. And then I will explain a two-matrix generalization of this algebra, which is just an algebra that depends on two numbers, n and m, little n and m. And this is the non-commutative algebra which controls two matrix correlators. And then I will talk about the structure of this non-commutative algebra and how it is related to Littlewood-Richardson coefficients. Basically, if you look at this algebra, it seems like it knows a lot about Littlewood-Richardson coefficients. And I'll explain in what sense it knows a lot about these Littlewood-Richardson coefficients. And then the motivation for applying this algebra to this problem in quantum information is that there were some intriguing identities about Littlewood-Richardson coefficients which were needed in quantum information theory. So I will explain what that application in quantum information theory was, and how did we prove it, and how did we generalize the proof of these identities. That's the plan. Okay, so let's think about a problem having to do with matrices. You have one complex matrix Z, which is size n by n. It transforms under Un in the adjoint representation. So Z goes to UZ U-tag. So you can think of Zij's, the matrix elements of Z, as variables, and there's a set of matrix variables. And you can ask, what are the polynomial functions of these Zij's which are invariant under this conjugation? And well, from physics, working with gauge invariant theories, we know what these things look like. If you take traces of it, from, for example, trace of Z cubed, trace of Z squared, and single or multi-traces, they are all invariant under this conjugation. And one interesting observation already is that at n equals 3, we observed there were, in S3, there were 3 distinct conjugacy classes, and there are 3 distinct traces. So what's the reason for that connection? The reason for that connection is that you can take, if you want to build gauge invariant functions of a matrix, let's say you have n of them, little n of them. While they are gauge invariant, so the indices must be contracted. The indices appearing here must appear below, and you have to sum these indices to build something gauge invariant. But the order of the indices, if you fix the order above, the order of the indices below is arbitrary. And this arbitrariness is captured by a permutation sigma. So given any permutation sigma in Sn, you can build a gauge invariant function, or gauge invariant polynomial function of the Z matrix entries. Now, because of the bosonic statistics of the Zs, these Z variables are commutative variables, you can move them around, and that moving around corresponds to a relabeling of these indices. And that relabeling is itself given by a permutation gamma in Sn. And as a result, if you think about how that gamma modifies the sigma, it turns out it modifies it by conjugation. So O sigma of Z, this gauge invariant polynomial, is the same as the polynomial I get by conjugating sigma. So the permutation description has some redundancy, which is captured precisely by conjugation with an arbitrary element of the symmetric group. So for each conjugacy class, therefore, you have one gauge invariant operator. For the moment, I'm going to take the size of n of the matrix to be large compared to the degree of the polynomial I'm thinking about. So in that case, all the conjugacy classes of the symmetric group correspond to gauge invariant operators, independent gauge invariant operators. In n equals 4 super Yang-Mills, there is a gauge invariant operator. This gauge invariant operator, which is made from a complex matrix, is a half BPS operator. It is annihilated by half the supercharges. And it is very interesting to compute the two-point function of an arbitrary multitrace operator with an arbitrary multitrace operator which is made of Z data. So the operator itself is described by a permutation. So what is the correlate? I've dropped the space-time dependencies here, so just the combinatorics. Well, the answer, the whole entire large N expansion of this correlator is nicely expressed in terms of these same permutations. What you do is you take sigma 1 and sigma 2, you sum, you bring in another sum over gamma, which is a permutation in Sn, and you multiply sigma 1 gamma, sigma 2 gamma inverse. This sum comes from Wick contractions, basically. And then you look at what that permutation, that product permutation is. Let that be equal to sigma 3. The delta function just says that this product of permutations is 1. So in other words, I'm taking a permutation which is equal to this, the inverse of this, and I take that and I raise n to the power of the number of cycles. So this is a completely algebraic description of the correlator of these multi-trace operators. So it's good to look at, that formula because it has a lot of interesting information. So what is the leading large N term here? The power of n is just the number of cycles of sigma 3. So which permutation has the most cycles? Well, that's the identity, because every number is in a single cycle. So when sigma 3 is the identity, what this equation is telling you is that sigma 1 and sigma 2 are conjugate to each other, because this times that is 1. And that tells you the trace structure of this and the trace structure of this are the same. And this is what is called factorization of trace, large N factorization. That the two multitraces are the same. So a trace Z cubed will mix with a trace Z dagger cubed and so on. So sigma 1 and sigma 2 will be the same at large N. But at subleading orders in the 1/n expansion, basically all we're doing is we're multiplying permutations. And in fact, we're multiplying conjugacy classes. You could show that, as we said, the operator only depends on the conjugacy class. So it only depends on these partitions. So what is this correlator? You just take sum of permutations in a conjugacy class, sum of permutation in that conjugacy class, and look at what outcome you get here, what sort of conjugacy classes you get, and for each of them you count the number of cycles, and this is the formula for the two-point function. Now this was all the description of the counting I gave was for the case where n was less than n. As we know, as you may know, when the power of the z inside the traces or in the multi-traces exceeds n, the counting is a bit more subtle. And it turns out that this subtlety can be completely captured once you go to this Young diagram basis for the center. So the Young diagram basis for the center was that we could build these central elements by summing permutations with a character. And correspondingly, for each sigma, we had a gauge invariant operator. So for each gauge invariant operator built out of sigmas, we could also correspondingly sum them with characters to build what are called Schur polynomial operators. And it turns out that at finite n, in this Young diagram basis, all the trace relations are very easy. They just say that any Young diagram which has a length that is bigger than capital N identically vanishes. So the finite end counting and the finite end construction of operators is just obtained by changing basis in the center to Young diagrams and then putting a cutoff on the Young diagrams. And this is kind of a lesson which works for both for one matrix and multi-matrix counting. And why does it work? The reason it works, it comes from something called Schur-Weil duality. What Schur-Weil duality says is that if you take the fundamental representation of UN, that's a representation of dimension n, basis E1 equal to En. Now if you take the tensor product of V sub capital N to the power little n, this is a basis, this is a vector space of dimension capital N to the power little n. Basis looks like this, tensor products of these EIs. And on this you have a diagonal action of the unitary group, U tensor U tensor U. So this makes this vector space a representation of UN. So this was, by definition, the fundamental representation. Take the tensor product, it's also a representation. Now, this representation is highly reducible. You can decompose it into different irreducible representations by organizing it into symmetry types, which correspond to Young diagrams. In Schur-Weil duality, what is important is that this UN action that I showed you commutes with a permutation group action. So if you take sigma, you permute these factors sitting in these different tensor factors as such, then this action of permutations commutes with this action of UN. Good. So therefore, one consequence of that is that when I decompose the tensor power of the n-fold tensor power of the fundamental, I get, of course, unitary representations of different symmetry types, but the multiplicity of that is directly controlled by a dimension of a symmetric group representation. So what that means is that in this vector space, where you have EI1 tensor EI2 tensor EIN, that's one sort of basis for this space, Vn tensor little n. There is another basis which is labeled by Young diagrams. And for each Young diagram, you have a representation of UN. Of course, if you have a representation of UN, you have a state in that UN representation. But for the same Young diagram, you also have a representation of Sn, little n. And there is a state in that representation. So what this tells you is that this vector space has another basis which is labeled by Young diagrams, but more specifically by two representations, one of UN and one of Sn. And this MR has the MR goes from, let's say, 1 up to dimension, the UN dimension of R. This little MR goes from 1 up to the Sn dimension of the same Young diagram. And there are concrete formulas for this, for both this one and for this one. And what this Schur-Weil duality, one of its implications is that the dimension of this n to the little n is the same as the sum over Young diagrams, the dimension of the UN times the dimension of the Sn. Because I have a tensor product, the dimension of this is the product of these dimensions. And then there's a direct sum, and then there's a tensor product. So the consequence here is that the dimension of this is the product of symmetric group dimensions and UN dimensions. And for the finite n question, what is important is that this Schur-Weil duality statement holds when n is perhaps bigger than capital N. But all you have to do is put a cutoff on the length, on the height of the Young diagram. the Young diagram cannot have more than capital N rows. So this is a very general fact. Whenever you're dealing with multiple indices, like in this, in this one matrix problem, you have the fundamental tensor to the little nth power. Even for multi-matrices, you just encounter things like that. And this is something general about how tensor powers decompose in representations of unitary group. And once you use the Schuval duality, there's a simple way to describe the finite n in terms of these Young diagrams. Good. Now, you have the basis of, I mentioned finite n operators. Basically, finite n operators are the Schur polynomial operators, which are labeled by Young diagrams. But what is the nice property of them is that if you compute the two-point function in the free theory, which is also equal to the computation in a matrix model, that two-point function is diagonal. So whereas multi-traces mix in the 1/n expansion, the Young diagrams do not mix. Two Young diagrams have zero correlator if the Young diagrams are different. And there's a normalization factor, which is easily expressed in terms of the structure of the Young diagrams. You have a product, there's one term here for each box in the Young diagram. The boxes are labeled by the row I, column J, and you have n plus j minus I. You take this product. So that's the answer for the two-point function of these Young diagram operators. And there's this orthogonality, which is important. So that's how, but you see, somehow there are matrices here and so on. Basically though, it's all about just the algebra, which is the center of the symmetric group, which is described in terms of either cycle structures or Young diagrams. So it's all really happening here in this algebra, sigma. It's all about sigma. The matrix itself is a distraction. What is really going on is linear combinations of permutations. And the correlator itself is entirely in terms of permutations, and the finite n is in terms of this Young diagram basis for permutations. The right-hand side is in terms of properties of Young diagrams, and so on. Of course, you have to do the matrix integral to get the answer, but at the end, the structure that comes out is a lot about the algebra of permutations. So. Now I want to talk about the two-matrix version of this story. What kind of algebra comes up? There's now a two-parameter. What is these two parameters? Well, when we were looking at polynomials in the z variable, we had to decide there's little n copies of z. Now we can have some number of, let's say, two matrices x and y, some number of x's, some number of y's. Here n equals 2, m equals 2. So we're going to have a family of algebras labeled by these two integers, which have to do with how many x's and how many y's. So what is the problem? You have two matrices x and y, which transform under un as x goes to ux u dagger, y goes to uy u dagger. They are both adjoints of the same un. You want polynomial functions in these matrix values, which are invariant under this simultaneous conjugation. And if you look at polynomials of degree n in x, degree m in y, you know what these gauge invariant functions look like. They look like traces or multi-traces. The subtlety now is that within a trace, you can have different orderings of the x's and y's, and that results in a large new multiplicity. But again, all of that is going to be controlled by an algebra, a permutation algebra. How do we get to the permutation? Well, if you have n copies of x and m copies of y, you just label the indices I1 up to in, n plus 1 up to n plus m. It has to be gauge invariant, so these indices must be, I1 must appear somewhere here, I2 must appear somewhere here, but the ordering is arbitrary. It's parameterized by a permutation sigma, which is a permutation of n plus m objects, these n plus m indices that acts on these n plus m. And you have a gauge invariant operator. But Again, the x's are bosonic fields, so you can reorder them without changing the function we're looking at. You can reorder them here. So that's a reordering which is in the subgroup of all permutations. It's a reordering in Sn times Sn. And if you do a conjugation of sigma by this permutation, by some permutation in Sn times Sn, you find that you have that really just changing the permutation this way amounts to basically reordering the x's and the y's. The gamma is something in Sn cross Sn, so it includes permutation that mixes the x's with the x's, the y's with the y's, but not the x's with the y's. So this is how you can describe a general two-matrix invariant. So the key thing here is what is the equivalence? It's a bit like conjugation, except you're conjugating by a subgroup. So therefore, there is an algebra which depends on n and m. It's the subspace of symmetric group on n plus m objects. The subspace of the group algebra, by this I mean the group algebra, arbitrary linear combinations of these things, which commutes with the subgroup. Turns out that the subgroup of this, the subspace of this, which commutes with this subgroup, actually forms a closed algebra. So it's not just a subspace, it's a closed subalgebra. And that subalgebra is, we're going to call it A and M. Now, how do we build elements of this algebra? Because we're trying to build things which commute, basically you take any permutation in this big group, conjugate with the subgroup, you get something which commutes with the subgroup. But it will not necessarily commute with a general permutation in Sn plus m. So that's why this is now a non-commutative algebra. This A and M is a non-commutative algebra. It is associative, and it has another nice property, is that there is a symmetric pairing, a non-degenerate symmetric bilinear form. So these are all properties that are inherited from the parent algebra. So we have a nice two-parameter algebra, non-commutative, associative, and an algebra with all these properties is called a semi-simple algebra. And there are some general things known about such algebras. So what is that? There's one useful general thing known about such algebras, and I want to describe that property. Actually, it's a property that you know from groups, but it is actually generalizable to these semi-simple associative algebras, which have the same property. So a nice property of groups is that the order of a group is the sum of squares of the dimensions of all its irreducible representations. But actually, this is a nice property. Well, for example, for a symmetric group of n plus m, the order n plus m factorial is the sum over all Young diagrams of the squares. But of course, associated with the group, we have a group algebra, which is arbitrary linear combinations, and the dimension of that group algebra is, of course, the order of this group. Now, this group algebra has a bilinear form. And what it is a pairing of sigma 1 and sigma 2, which comes from the delta function. Basically says sigma 1 equals sigma 2. If sigma 1 equals sigma 2, the pairing is 1. Sigma 1 not equal to sigma 2, pairing is 0. So there's a nice pairing in the group, which can be lifted to the group algebra. And in the group algebra, it gives a non-degenerate symmetric bilinear form. Bilinear because now you're allowed to take linear combinations of these things. So it's a nice non-degenerate symmetric bilinear form. So what is known about algebras, any algebra with these properties, is that the dimension of that algebra has to be a sum of squares. So in fact, this is an example of that. This is the dimension of the group algebra, and this is a sum of squares. It is a sum of squares of what? Well, the dimensions of the irreps. So this A and M that we talked about is also an algebra with all these properties, associated with a bilinear form. And when you have such an algebra, its dimension must be a sum of squares, and that sum of squares can be written in terms of Young diagrams. You take a Young diagram with little n boxes, a Young diagram with little m boxes, a Young diagram with n plus m boxes, And then you take what is called the Littlewood-Richardson coefficient, which is kind of a number having to do with how many ways can I put together this Young diagram with n together with the m to build Young diagram R3 with n plus m boxes. The multiplicity is called G, the Littlewood-Richardson coefficient. And this algebra has a very nice property that its dimension is the sum of squares. Okay? And there are some deeper implications of that. So what is this Littlewood-Richardson coefficient? It's a number of ways of putting together Young diagram R1 with little n boxes, R2 with little n boxes, to get R3 with n plus m boxes, subject to some rules. Details are not important. They are Littlewood-Richardson rules. Now, there are two group theory meanings for this Littlewood-Richardson coefficient. One is this Young diagram R1 and R2, they correspond to two irreducible representations of UN. If you take the tensor product of that, and there's a diagonal action of UN, the same U acting on both, you decompose this in terms of this diagonal action, you ask, how does that correspond to irreducible, which irreducible representations appear? Well, there will be those irreducible representations, R3, which correspond to Young diagrams with n1 plus n2 box, n plus m boxes. And the multiplicities with which these, if you have an R3 in this tensor product, it could appear more than once. These multiplicities are what are called the Littlewood-Richardson coefficients. But it's very important and interesting that these same coefficients have a meaning just purely in symmetric groups. And that is a consequence of Schur-Weil duality as well. So you take a Young diagram with n plus m boxes, it corresponds to a representation of this group, an irreducible representation of symmetric group with n plus m, symmetric group on n plus m elements. This has a subgroup of Sn times Sn, which is permutations of just the first n and the last m. Just like we had in the two matrix problem, the gamma, it lived in this subgroup, permutations of the first n things and the last m things without mixing. So if you take an irreducible representation of this big group, and you ask, how does it decompose under the subgroup? Well, in general, something which is irreducible under the big group will become reducible under the subgroup. So the subgroup representations are given by pairs of Young diagrams, and the multiplicity of that is given by the Littlewood-Richardson coefficient. So the same number, which has a role in the tensor product of UN, also has a role in reduction of Sn plus m. That's just a mathematical fact. It follows from Schur-Weil duality.
So just to be sure, so is there a closed formula for Littlewood-Richardson, or is it only for specific classes of Young tableaus that there's a closed formula?
Yeah, I wouldn't say that. There's an algorithm, but not a closed formula.
But given any...
Well, I suppose, well, there is a formula in terms of sum of characters. That you have something like G, R1, R2, R3, the Young diagram with n, m, n plus m. So you can take sigma 1 in Sn, sigma 2 in Sm, 1 over n factorial, m factorial. Take the character of sigma 1, character of sigma 2, character of sigma 1, outer sigma 2. So this acts on, this is a representation of the big group. You can let this act on the first n, so the first last m, but that whole thing is a group element in Sn plus n. You can take its character, and that's a formula for the multiplicity. But there's sort of a sum of n factorial, and there are algorithms for this. So in fact, computer scientists want to know, is this like a hard problem or easy problem? And it's actually a hard one in sort of computational. If you for large n and m to explicitly calculate it, it's a NP hard or something. So to get an explicit formula is hard, but at least it gives you a conceptual understanding. This formula here gives you a conceptual understanding of the counting of two matrix operators, because it's the sum of G squares. So in here, there is no capital N, which is the size of the matrices. But that's just because I've taken little n and little m to be small compared to capital N. But the finite n effects, as before, are easy to take into account once you have the Young diagram description. It's just that the third Young diagram here should have a height which is no bigger than capital N. So there is a formula for the finite n counting of all the states in terms of these little Richardson coefficients. Again, to make that explicit, it's a bit hard, but there is a formula. So I've convinced you that this algebra is useful for counting gauge invariance of two matrices, both for large N and finite N. It also gives rise not just to counting, but also an explicit basis for these two matrix invariants. Those of you and many of you here have worked with restricted Schur, so you will know how to explicitly build this basis, and you also know that these give orthogonal free field two-point functions. So the moral lesson here is that these algebras are good for counting, but they're also good for free field correlators, and there's a nice interplay between weak contraction combinatorics and this description of gauge invariance using permutation rules. If you want to see the details, you can look at the reference I mentioned earlier. So just a little bit more on these algebras. So basically, associative semi-simple algebras are isomorphic to that. So why is it the sum of squares? Why is the dimension of the algebra the sum of squares? That's because the structure of the algebra has to do with algebras which are matrix algebras. A matrix algebra, the dimension of a matrix algebra is the square of the size of the matrices. So in fact, you take this group algebra Sn, we said that's n factorial sum over dr squared. So you can actually build a basis for the group algebra of Sn quite explicitly. Qrij is labeled by R, which is an irreducible representation of Sn, I and j, which are states in that representation. You can explicitly build something in the group algebra just using the matrix elements of sigma in some representation in an orthogonal basis ij. You can build something, linear combination of permutations, which multiplies like matrices multiply. You know, if you have an elementary matrix with 1 in the ij slot, elementary matrix 1 in the kl, it multiplies like this delta jk and then qil. So this matrix structure of multiplication is what is responsible for the sum of squares. And this is called the Wedderburn-Artin structure theorem for these algebras. For example, you have nice online notes on this business. So the algebra, the dimension of the algebra is the sum of squares, and you can actually have a nice basis which reflects the matrix structure of the algebra. And the same holds for this A and M. This was a sum of squares, which was a sum of squares of Littlewood-Richardson coefficient. And the explicit formula is not important. It comes from the restricted Schur construction. Not important for what I'm doing today. Okay. So basically, this algebra controls everything about the counting and correlators of two matrix invariants. And the interesting thing is that it has some, and also its structure is related to Littlewood-Richardson coefficients in a very, it has matrix blocks. This algebra is a direct sum of matrix blocks. The size of these blocks is the Littlewood-Richardson coefficient. So if you see an identity like this, here's an identity which comes up in quantum information theory. R is a Young diagram with little n boxes. So there's an identity. You take the dimension of that Young of that symmetric group representation times n plus 1, and then you take a sum of a Young diagram with n plus 1 boxes, and then this is the dimension of the representation of the symmetric group with n plus 1 box, dimension of the representation R of the symmetric group on n plus 1 elements. And this is a Littlewood-Richardson. It couples representation of Sn along with a single box representation of S1. Tells you how many times R tensor box contains R. These numbers are either 0 or 1. And this is called a content of a box. So when you put together Young diagram with n minus 1, with n boxes, and then you put in another box to build something with n boxes, that box has a location somewhere. The content is basically the row minus the column of that extra box. And this content here, you take the square of that, you do that, and it turns out this is an identity that is important in quantum information theory. And I'll explain why it's important. I'll outline roughly why. But we have an algebra which seems to know a lot about these Littlewood-Richardsons. So you would think maybe the algebra knows why this is true. And that is indeed true. So again, it involves understanding why that identity is true. It involves the following things. We're going to exploit the fact that there are two meanings to this Littlewood-Richardson coefficient. How many times? There's a meaning in terms, as we said before, in terms of the unitary groups. Take symmetry type R for unitary group representation, a single fundamental, tensor it, decompose it in terms of representations, and you will find that this is the multiplicities of unitary representations is given by the Littlewood. But when you have a fact like this, that means the dimension of this, which is the dimension of UN representation with R, times the n, which is the dimension of the fundamental, is equal to the sum over representations with n plus 1 boxes, Littlewood-Richardson type dimension. So that's one identity. But this identity, of course, you can make it more explicit because there's a formula for the dimension of the representation of UN divided. So if you look at this formula, if you look at this formula here, if I divide on both sides by this quantity, I will get a ratio of dimensions. And it turns out that that ratio of dimensions is related to symmetric group dimensions, along with something, a polynomial, which is related to capital N and the contents. So now if you take that equation and you just write it down, you can deduce the following fact. So you see this is a polynomial in N, and this is just N. So the leading order must agree on both sides, and the subleading order must vanish. So you get a vanishing. So this is one equation, just from this fact. So we got an interesting equation just by looking at this identity and then comparing dimensions. But we want to do something a bit more general. So how can you do something more general than comparing dimensions? Well, the dimension is the trace of one. So what you can do is take a trace of something else. So one thing you can do is take a representation like that, tensor with n factors, with the fundamental, decompose that in terms of using Schuh-Weil duality, and then in that representation, it is useful to think about this kind of element in this A&M. So this is an element in this A&M algebra, and you can calculate the trace of that in tensor space. Turns out there are two ways to calculate the trace of this thing. One is kind of this projector is a sum of permutations. You're multiplying it with another permutation, so you can count how many cycles in that product, and then you're taking a trace in this vector space. So when you take that trace, you get n to the number of cycles. It's the kind of thing we use in correlators. But there's another way you can calculate the same thing. The other way is to take the same object x, which is a projector times the sum of things here, sum of permutations. You can recognize that sum of permutation is a difference of these T2s. Sum of all swaps in Sn plus 1 minus swaps in Sn. So that's the element we chose. And then you're calculating the trace of that in tensor space. And tensor space is this tensor product, which has a direct sum decomposition in terms of Young diagrams. And I can insert a sum of projectors onto all Young diagrams here. So in other words, this is a representation theory way of calculating the same trace. Just recognize that your tensor space is a direct sum of Young diagrams of n plus 1, W is n plus 1 tensor. So if you decompose that in irreps of Sn plus 1, there'll be Young diagrams there. And so you look at this way of calculating that trace, and you find another formula for the same trace. And if you compare the two formulas for the same trace, you find the identity that, as I mentioned, was useful in quantum information theory. So why was this useful in quantum information? So this was useful in connection with no cloning. So in quantum information, there's something called no cloning theorem. You can't exactly clone a state. So there is no unitary operator in H, tensor H, which acts on the tensor product of arbitrary normalized states. So phi and E are normalized states in H, and you have a tensor product. You can ask, can I clone phi? So can I have an operator, unitary operator here, such that when I act on phi tensor anything, the output is just phi tensor phi up to some phase. That depends on the things I put in. So is there a unitary operator that will take phi tensor E to phi tensor phi? So no cloning theorem says that there isn't such a thing. So what people in quantum information theory have tried to understand is different versions of approximate cloning. So you can't exactly clone a state, but can you approximately clone it? And likewise, you can't exactly clone an operator. So you have a quantum device which performs some unitary transformation on a Hilbert space. Can I reproduce that unitary transformation? And you can't because of no cloning. But there's some notion, there are a couple of different notions of approximate cloning. And so what approximate cloning, you can sort of understand what it is. You're trying to reproduce some operator U. Can I get something near U? That's one thing. So you can try and say, if I can't exactly clone things, but can I produce something which is as close as possible to the U I start with? Well, that's a fairly intuitive thing. But there's something else which I've never heard of before, but which is called perfect probabilistic cloning. What you're trying to do is you have some operator U which acts in a device. So you have some operator U, and you have some quantum device where U acts, let's say, n times. You know it has acted n times. And as a result of this action, there was some input state, and there's an output state, and you know what, given the input state, you know what this thing is. The effect of acting on you with this device, where it has acted n times, you produce something. Now you don't have you, but you know what this state was, you know what the thing was, and you know what the outcome of this device was. And using this information, now given some general state, I want to do the best I can to produce U times Xi. So these guys are thinking about a problem which is called storage. So they act in some device, and then you store this outcome. And the task is to take that outcome and retrieve in the best possible way the action of U on some general state in the Hilbert space. And there is something called perfect probabilistic cloning, where so you have some next stage device which has two outputs. One is a classical output, and the classical output will tell you either success or failure. If it says failure, then you shouldn't trust the answer. But if you say you get success, you know that this will correctly reproduce UXC. So this is called probabilistic. It doesn't always work, but when it works, it gives the right answer. And one problem these guys are interested in is if you have a perfect probabilistic scenario for storage and reconstruction, what is the best probability of success that you can hope for? And so that's a kind of optimization problem, and this is what they found, that if you have little n uses of the unitary operator in a quantum device, and the Hilbert space is of dimension capital N, the optimal probability of success in this kind of perfect probability. It's called perfect because if you get an answer that you can trust, you know it will be the right one, it will be the perfect answer. So in this perfect probabilistic reconstruction problem, what is the optimal probability of success? It will depend on how many times you have used your unitary operator in this initial storage device, and it will depend on the size of the Hilbert space, capital N and little n. And the optimal probability of success these guys proved is this thing. And they proved it, and in order to prove it, they required this identity. This had to be true for them to be able to prove this bound on the success. And so one interesting thing is that the proof that we gave for this identity that was crucial, basically it used some properties of this algebra, AN1. But if you do the exact same steps and you just change the x you were thinking about slightly, you find, and instead of working with AN1, the algebra that we know, which has to do with n matrices x and 1 matrix y, now you use it for n matrix x and m matrices y, you find a new identity which generalizes the previous one. It has a product of dimensions of Sn and Sm, Littlewood-Richardson coefficient, these contents of Young diagram boxes. So this generalizes this guy. So one conjecture is, a natural conjecture, is that if you generalize this quantum information optimization problem, where you're using your unitary operator n times, but you're trying to reproduce at the end the action of that unitary operator on some m-fold tensor product, then there will be the analogous optimization problem, and the natural conjecture is that this NM identity will be useful in finding this optimum probability there. And this is a conjecture that we made together with this quantum information expert, and this is still open. We don't know what is the optimum probability. We don't know all the steps to really prove that this identity really leads to that. But in the N1 case, it is true that you know the optimal probability and you know how to prove the key identity using the algebra AN1. There are other generalizations coming from the matrix theory perspective. There was the NM, this has to do with basic, but there are other very similar algebras. In matrix theory, this has to do with N1 copies of one type of matrix X, N2, X, let's say X1, X2, X3 up to Xk, K different types of matrices, and these K different types of matrices. You fix how many X's and Y's and so on you have, and you can engage invariance. There's an algebra that controls that. In that algebra, there's a natural element. It turns out it is a central element in that non-commutative algebra, which generalizes what we did, and you find another generalization. This one, there's no obvious guess at the moment what kind of quantum information problem. So there were two numbers here, N1 or Nm. This had to do with the two steps: storage quantum device and retrieval quantum device. So there are two steps in this optimization, quantum optimization problem. But if you have kind of k devices, we don't know exactly what problem makes use of this identity, but it's kind of would be interesting if one could find such a thing.
Are your G's there still called Littlewood Richardson?
Yeah, basically you could do it in step R1 tensor R2, and then tensor, yeah, just R1 tensor R2 tensor R3.
So the multi-G's can be expressed in terms of the usual...
They can be expressed in terms of the usual ones.
By doing it in steps.
That's right. By doing it in steps, you get the usual one. So there is no obvious generalization of the perfect probabilistic storage retrieval problem, because the storage retrieval problem is something that involves two numbers. But there might be some sort of multi-partites, where instead of two devices interacting, there might be multiple devices, where perhaps the same kind of thing, identity, can be used. And then here's a speculative comment. No cloning has been discussed in the context of black hole puzzles, ADS-CFT. So here's a concrete, approximate cloning task that quantum information theorists have thought about. There's this perfect probabilistic storage retrieval problem that they have thought about, and they have concrete things to say about the best we can do in these different kinds of approximate scenarios. So is there some interpretation in the context of black hole puzzles or ADS-CFT of these particular quantum information tasks? And also, David Berenstein has related the two-matrix problem to some ideas about small black holes in ADS-CFT. And the question is there an interpretation in this setup of the link that we are finding between two-matrix combinatorics and this perfect probabilistic reconstruction, a link which is being provided by the algebra, which controls these correlates. So these are some things one can think about. And so this is one example of sort of ideas from holography, which have to do with matrix combinatorics, but an algebra underlying that, which has applications to information. So in my next talk, I'll talk about some other application of sort of similar representation theory methods, and so I'll stop here for today.
Questions for Sanjay?
Yeah.
I want to know more about product rule of Schur polynomial using Richardson.
Product rule of Schur polynomials.
In terms of Richardson.
Yeah. So basically, the product rule is basically the Littlewood-Richardson coefficient. So if you have a Schur polynomial chi R, chi S, Z, it's you can write it in some chi T. So if you the coefficients that appear here are the Littlewood-Richardson coefficient. And the explicit rule has to do with, you take the Young diagram R, and then you take the Young diagram S, that is some particular one. What you do is you're going to kind of align these guys together and produce something with n plus m boxes. And the rule tells you that the way to do it is just label these guys, let's say ones, 2, 3. So everything in the first row are ones, everything in the second row are ones. So. And then you take, you stack it together with the first one. Let's say put a 1 here, and the next one here, and 2 here, a 3 here, whatever. And the rule says that when you have done that, the numbers that you see here should have satisfy two conditions. One is they should be weakly increasing along rows and strictly increasing down columns. Weakly increasing means they could increase or they could be equal as you go from here to there, but they can't fall. So it's weakly increasing. increasing or stays equal along rows, and strictly increasing down the columns. That's one part of the rule. Okay? And the second part of the rule is that if you read these numbers, read it from here, and then here, and then here, and you just write, 1, 1, 2, 3, 1, whatever, just read that thing. Then if you look at that sequence of numbers, at any point if you stop that sequence, you should have seen you should never have seen, like here, 1, 1, 2, I have seen more ones than 2s. That's okay. But you should never have seen more 2s than 1s. So the sequence that you read this way should satisfy a condition that if you look at the sequence and you stop it anywhere, you should not have seen more 2s than 1s, more 3s than 2s, and so on. So there are two elements. One is this weakly increasing, strictly increasing, and then this property of the word, this sequence of numbers. And that's it. And then if you do that in several examples, you'll see you'll correctly reproduce these numbers.
Other questions? Thanks, Sanjay, again. We'll pick up at 11:05.